All right, so my name is Mihai BAICEANU. I represent the Technical University of Civil Engineering in Bucharest. And today I'll be presenting my work entitled Experimental and Simulation Performance Investigation of a Hybrid PVT solar panel. So a photovoltaic and thermal panel which outputs both electricity and thermal energy. Just words about myself. I have a bachelor's in building services engineering, and I'm currently studying energy efficiency of building systems in my master's. And the work I will be presenting today was done in my first year of master's. I will start with why I think this subject is very, very relevant. Well, I think that solar energy is if we want to put an end to resolve the current climate crisis, I think solar energy is key. Um, and so all the directives and the Paris agreements and so on, they all say that. But solar energy also has a few problems. And the first one, probably the largest one, is efficiency. And I'm referring to normal photovoltaic panels. Their current, with the current technology, the global efficiency is about 15-20%. So about 80% of the energy that we get from the sun is wasted, and that is because it gets dissipated as heat. Of course, there's the problem of storage. We know that there are no really good batteries now, and also the problem with demand and supply synchronization, because we do get lots of solar power midday when we don't really need it that much. Also, a very important problem is the fact that these solar cells, of course, they like solar radiation, let's say, in the sense that when solar radiation increases, the electrical output increases accordingly. But as solar radiation increases, temperature also increases, and that leads to quite a dramatic drop of temperature, and we are talking of an average of 0.5% drop in efficiency. With every degree Celsius, we go above 25%. And as we will see, they reach up to 60 degrees Celsius. So this problem, this very big problem, is mainly solved by this technology, which is integrated photovoltaics with thermal technology. And there are many types of technology of integrated, the two, but the one I studied is quite a simple one with a water coil circulating beneath the photovoltaic cells, and of course insulation. The advantages of this technology are quite well reviewed by current literature. The obvious ones are less roofs, surface occupied, better electrical efficiency during the hot periods, because you do make hot water, but as a result you cool the panel, so its efficiency increases. Well, in the literature review, I noticed that most of the simulation studies that are trying to study whether this technology is applicable, is feasible for integrating in buildings or retrofitting buildings, they focus on not already efficient buildings. So most of the studies are either on substandard buildings, where really any retrofitting has a great result, or at best standard buildings, code buildings. So the big questions to answer is, are these type of technology viable from technical and economical standpoint to be retrofitted on very efficient buildings, solar buildings, nearly zero energy buildings? So the objectives, we started off with three main objectives. The one is analyze the efficiency experimentally of these panels, and this is the first part of my study, the experimental part. The second one investigates its integration on a building, on an actual building, and this is the second part of my study, simulation. The third part was going to be developed in 2020, but COVID restrictions unfortunately put that on hold. So today I'll be presenting and I will try to answer these two questions. These are my objectives. So for the first part, the experimental part, the experimental stand is quite similar. We have a hybrid panel and a normal photovoltaic one. They are subject to same external conditions, same external radiation, same orientation and tilt. We have the hydraulic part for the hybrid panel, a circulating pump and water tank, and measurement tools, an analyzer to measure electrical data for both of them, and one to gather temperature data from several points in this system, key points. And so I will start with the measures that we measured here, the data we acquired. So in order to measure the power output of the hybrid panel, the thermal output, we measured water flow, which was fixed during the experiment, and with thermocouples we measured temperature on the back of the panels, water inlet and output, ambient temperature, and we also measured temperature on the face of the panels with an infrared camera. With the electronical measurement tool, we measured IV curves, current voltage curves for both panels, and from there we extracted instant power during the experiment period. The experiment took place during 1 week in October 2019, and it's really important to state that it happened in October. That is close to the autumn equinox, when irradiance, solar irradiance data are average for a whole year. So that makes the weather conditions quite relevant for the outcomes and for a whole year. Yeah, that's myself there doing the measurements. I will get to the results of this first part of the study. First one is just external conditions. Here we have, as an example, one of the days of measurement with a quite clear sky, only short drops in irradiance. And here we get to the first really meaningful results. We see the temperature difference on the back of the panels measured with thermocouples. The difference is constant, quite constant during the day. It's a sustainable difference of 5 degrees Celsius. Of course, the hybrid panel is cooler because that water is cooling it. So we do expect to have greater electrical efficiency, to output more electrical power. And indeed, that was the case. The hybrid panel got during that day 10% more electricity, and these are the values here. I think 10% is quite an improvement, but this is not the only thing that the hybrid panel got. It also produced thermal energy. So we did get 2.1 kilowatts hours of thermal energy, hot water. Yes, I mentioned before we also did a thermographic study, and the objective of this was to see really, so we measured the temperature of the back of the panel, but we wanted to see radiative temperature on the face of the panel, and also the distribution of temperature, I think, is very relevant to the heat transfer and the current technology in these panels. And we can see some quite significant irregularities due to the water inlet and outlet effect. We can even see the coil here, the effect of the coil, some hotter areas, some colder areas. But something really interesting was that on the face of the panel, the temperature difference was even larger, was 16.5 degrees Celsius. That is the maximum one. So around midday, it happened somewhere around midday. Okay, so this was the experimental part where we checked practically how well the panel behaves in practical conditions. And next, the simulation. Um, I stated that the objective of this study was to see how well it integrates and is it technically feasible to be implemented on a very efficient house. And we chose house FDM signature. It was the representative of Romania in a solar decathlon contest in 2018. I was part of the team of students that built this house. I was the coordinator of energy efficiency and mechanical systems. This is a fully solar house. It's now being certified LEED Platinum. It is a nearly zero energy building, and so we chose it as a reference building to do our simulation studies. Um, the simulation procedure is as it follows. We used two simulation software. The first was Design Builder, which we used to, we modeled the building with its geometry and the thermal properties of the envelope as well as shadings. The house was designed for Dubai, for the Middle East, and this is why there's lots of shading. We use this to calculate heating loads, cooling loads, to be then inputted as inputs in this software, Polysun, which is more suitable for the simulation of solar panels, photovoltaic, thermal, hybrid ones. They do have a really large library of equipment, and that is why we chose it. But it is also a dynamic simulation, so you do input a weather file and it calculates dynamically during a year. And so this is why the data is very, very relevant. This was the methodology. We studied the integration. We studied two systems. We compared them. One with separate photovoltaic here, photovoltaic and thermal panels. They are separate in the first situation, and the second situation when there's hybrid panels. The rest of the system is the same combined production of hot water for heating and domestic hot water. There is an efficient gas boiler, radiant heating, loads of the house, loads from electrical consumers, electrical storage, and connection to the grid. This part is the same. What differs are only the panels. And these are the results after simulating a whole year of that house with panels in Bucharest. The first one that is very relevant, I think, is the total electrical energy of System 1 and System 2 that they produced during that year. With the blue, we have the separate situation, and with green, the one with hybrid panels. And the result was that indeed the variant with hybrid panels outputted 5% more electrical energy during a year. Yes, during a year. The second unit that we calculated that is more relevant from an economic standpoint is how much that house consumed from the grid during that year, both electricity and gas. So that would be what the final client, the inhabitant, pays. So this can be translated in money. And the situation with the hybrid, we have a significant drop in costs, in consumption of 11.1%, which translates into basically almost half a ton of CO2 per year. If we take into account transformation into primary energy by Romania's standards. We can see that this house is very efficient because during summer we can even feed energy to the grid. It is designed specifically to be able to inject electrical energy into the grid, which is technically feasible, not legally yet in Romania, unfortunately. Okay, and these type of results were similar to ones in literature. So these were my results for the experimental part, for the simulation part, and in relation to the objectives, which I stated in the beginning, we have these conclusions. We can draw these conclusions, and it's just a recapitulation that we noticed experimentally important temperature difference between normal photovoltaics and hybrid photovoltaic thermal. The electricity yield during an average day of the year is 10%. We also produce thermal energy which can be used to prepare domestic hot water or for space heating. And the average would be about 2 kilowatts per panel. So if you have a whole array, that value is way larger, of course. And the thermographic study shown these irregularities here, which mean there is further research opportunity to further study this and improve heat transfer here. This was the experimental campaign, and now from the simulation part, basically the results in the experimental campaign were basically validated through the simulation campaign, because we also got, by simulating a whole year dynamically, results of hybrid panels producing more electricity by 5%. And probably the most interesting result is a drop in consumption for such a solar house that we showed of 11%. These are my results. These are the results of my work, and I think seeing all of these, we can conclude and we can agree that this implementation of panels is feasible, even for already very efficient buildings, from a technical standpoint and from an economical standpoint. Which takes me to my last slide of this presentation. What I presented today was phase 1 of research, which also got us, me and my coordinating professor, on a paper published last year. And also last year was the year when we were supposed to do phase 2 on the study. But because of severe restrictions in Romania, our university got shut down, all universities in the country. We weren't able. This was the phase to actually take the simulation part of my research into experimental and use that house to install an actual photovoltaic array and calculate during a whole year, not just a week like in the experimental study, but for the whole year, how it behaves actually installed on the house. And we wanted to see if that also confirms what we got in the simulation here. But I'm quite hopeful that that this pandemic is close to be over, and we will also do that. So thank you very much for your attention. I'm very grateful to be able to have presented today for so many people from all over Europe, professors and especially fellow students, so many young engineers there. So I thank you, and I'm waiting for your questions. Thank you.